Sir.
Sir.
Start.
Okay. Thank you. Good afternoon, everyone. I am Chandra sir from GKD ATR. First of all, thank you very much for joining this webinar during this pandemic time. We will start this webinar shortly. Meanwhile, let me take this opportunity to introduce our GKD ATR. GKD Institute for Technological Resources is a unit of GKD Charity Trust, Coimbatore. It was established by late Cavalier Dr. D. Jayavardhana Velu, former chairman, Lakshmi Mason Works Limited. For the first time in our country, GKD ATR is tied up with Tata Institute of Social Sciences and Alagappa University for commenced university model degree level technological skill development programs in the domain of manufacturing, automation, and foundry technology. Moreover, GKD ATR has FANUC India certified CNC and robot training for training CNC and robots. Over 80,000 trainees from GKD ATR have secured jobs in prestigious companies in India and abroad. At the end of this webinar, kindly I request you all to submit your valuable feedback and receive the participation certificate. Now, I request our director, Dr. Balamurugan M, to give welcome address for this webinar. Welcome, sir.
Welcome everyone. Thank you for joining us for today's webinar, Integration of Supply Chain Management and Additive Manufacturing. The mission of doing this webinar is, today manufacturing is changing faster than ever before, and drivers for this include globalization, individualization, time to market, and sustainability. Furthermore, what will be the future of manufacturing if we compare it today's manufacturing? If you observe, time to market today is time intensive. In future, it will be instant delivery. Further, when we look into the innovation, today is a product-based innovation, but in tomorrow, it will be solution-based as well as shift to consumer-oriented innovation. Next, when we look into the operational process visibility is limited today. In future, it is going to be across value chain ability to track behind the scenes. When we look into our production today is mass-based production. In future, it will be personalized and personalized solution at scale. When we look into our customer engagement, today is a death of royalty. But in future, it will be using brand loyalty and competitive advantage. Finally, when we look into our delivery accuracy, today is error prone, but in future, it will be zero defect. How to overcome these gaps? First thing is first, this additive manufacturing, it is not a new technology, nor it is a business discipline. Additive manufacturing could reduce the energy used by 50% and reduce material cost by up to 90% compared to today's traditional manufacturing. I believe that by participating in this webinar, we are in the right place and right time. Together, let us accelerate the exchange of ideas and scaling up good practices. Now, without further delay, we will turn time toward the speaker. Our today's speaker is Dr. Rajesh Ranganathan. He has done a doctorate in manufacturing management and supply chain management from Loughborough University, United Kingdom, and also domain expert in smart manufacturing, and additive manufacturing. And he had published more than 50 research articles on this subject. I'm glad to inform that Dr. Rajesh is Board of Studies member of GKD for our BWork undergraduate programs. I invite Dr. Rajesh to deliver this webinar. Dr. Rajesh, the floor is yours.
Very good afternoon, one and all. Very good afternoon, Director, sir, like Dr. Balamurugan. And thanks very much for your kind introduction. So having said that, I could see a good amount of efforts that are being placed in this, in organizing this event. And I thank yourself and the committee, whoever is involved in undergoing this webinar. And I would like to thank the participants for taking their time off on a Friday afternoon and being here for this knowledge sharing process. So with that kind note, I would like to get into the topic of integration of supply chain management and additive manufacturing. I understand it's an afternoon session. I would try to keep it as lively as I can, and we'll go through live examples. And when it comes to discussion, we'll have our discussions at the end of the session. Hope that's fine with most of the audience. So starting with the webinar, to give an overview of what we are going to look in today. So we'll start with a slight note on what is that happening in terms of manufacturing, or where is the shift which is happening, and where did manufacturing, or first of all, if is manufacturing and management getting integrated? If it is getting integrated, where and how it got integrated, and then we'll slightly move into additive manufacturing. I did happen to see the spread of audience over here, and so I thought I'll give a slight note on what additive manufacturing is, and a bit about, we'll see the types that are involved, the possible inputs that we can give. So with the overview of both supply chain and additive manufacturing, then we'll touch on the objectives and with some live case studies of the possible integration. So where did this shift in manufacturing happen? So we all know that when we go back to early days, earlier it was one highly skilled labor, wherein he tends to produce excellent pieces of work, or we can say excellent pieces of artwork. Here I have taken an example of a carpenter, wherein he had his own skills, and he produced one of a piece, or we can, in modern world, we can call it as customization. He produced one of a piece, and he gave it to that particular customer. And that was maybe like 200, 300 years before, or even before industrial revolution. So then came a situation of industrial revolution, and then we moved into mass production. And whenever once I was reading about where did this actual manufacturing shift took place. So I came across one interesting fact that we Indians, we played a major role in making the entire manufacturing to take a major shift, or in a way we were the people who made this innovation to come out in manufacturing. How I can say that is, we all know the story of East India Company getting into India. And when East India Company came into India, or when they were doing what they were doing, and the situation was they were in need of more amount of rifles as the protest was going up in India. During those times, like if we want to send the information from India to Birmingham, because or to London, it takes about 15 complete days for the information to travel from India to London. And then they would order for manufacturing the product, or when I say the product here is manufacture of rifles, but over there they were manufacturing, they had the potential to manufacture one rifle per day, but suddenly there was a demand for 300 to 500 rifles. Already it takes about 30 days for the information to go there, and once the information reaches, then they need to produce 300 to 500 rifles in a very short duration, and the product need to be shipped back to India. Well, while shipping it back, it takes about 30 days for the goods to come back to India. So we are speaking of roughly a timeline, hoping that the product gets done within 15 days. We are speaking about a timeline of the entire supply chain timeline of 2 months, which is quite a very vast amount. And this was the period wherein they thought that they can't cut on information, they can't cut on the logistics, but the only way they can improve is how they can improve the manufacturing. So a highly skilled labor, he can produce the rifles, more than one rifle per day. So that is the time period wherein lathe was uh, lathe came into existence, drilling machines came into existence. Much of the machineries that we are seeing now all came into existence. This is all which I read from a book called Gun Trade Birmingham, which is available in the marketplace. So that is where I came to know that we Indians were one of the initial triggers who brought in the idea of various manufacturing machines. So then came the situation of mass production, wherein Henry Ford coined the word, or it was otherwise it was called as a Fordism age. So Henry Ford brought over the idea of mass production, wherein he brought the idea of standardization, and whatever he produced the cars in black in color. And that is the period where a slight change started taking place. So people were not happy with all the cars which are black in color. So some people demanded, okay, I need some, I don't want to go for a black color car. I want a white color one. I want a red color one. I want a blue color one. So this is the first time that the term mass customization came into existence. They produced everything standard, but only thing is during the final touch, they changed the color of a car. So that is where mass production got transferred to a new terminology which was called as mass customization. So as mass customization started changing, or the manufacturing was changing, all these time we were involved in a process which was called as subtractive manufacturing, wherein if you want to produce a product, you take a bulk of a product, from that you subtract whatever you need and you use that final subtracted quantity as your end product. So that's why it was called as subtractive manufacturing. So all this time we were using or a concept of subtractive manufacturing, and this gave, as the production need to improve, or as the production started spiking up, there came the innovations or inventions and manufacturing techniques, like various types of machines came into existence. Fine, that's fine. All the machines are not sufficient. So then we moved on to automation, wherein we want to have a bit of a pressure and we want to go for mass production at a wider range. So that is where subtractive manufacturing got combined with mechatronics, and then came the age of automation. So that's why we were moving on. As we were moving on with higher production rate, then people thought like, okay, there we need some more things to come in, and that is why we started finding a shift in manufacturing. Manufacturing started changing a bit, and it started getting improved. That is the time period wherein manufacturing and management got integrated together. When manufacturing and management got integrated, there came so many terminologies, because they want to make sure the manufacturing happens through the entire supply chain or within the entire industry. So the manufacturing need to go smooth. So that is where many terminologies started coming up, namely the assembly line, batch production, mass production, process optimization, automation, time study, method study, just-in-time manufacturing, lean, agile. All these management terminologies started popping up. So this was the time era wherein it started finding a good integration of manufacturing and management. And that is where manufacturing and management started finding its integration. So yes, manufacturing and management, they had their integration in a way. Going back a bit, when we go back a bit, we could see that at the very early stage, there was only one manufacturer who was producing a component, and this was a high custom product, and then he was delivering that particular product to a customer. As slowly as time moved by, we could see a major shift in manufacturing took place and management took place, and obviously that led to so many transformations, or a complete transformation in supply chain started taking place. Like you had a bunch of manufacturers, then you had a set of wholesalers, and then it moved to the retailer, and finally the product moved to the customer. So it was no more from manufacturer directly, the product is not given to the customer, it took its own line. So there came a major transformation in supply chain. So wherein we called it as inbound supply chain and outbound supply chain, wherein anything that goes inside, if we take manufacturing playing its role in the middle, and anything that goes inside, it's called as inbound supply chain, and anything that goes outside towards the customer end, we call it as an outside supply chain. And ideally, if we take any supply chain, there are three flow lines which goes by. One is the material flow line, other one is information flow line, and the final one is the money flow line. I'm not going to touch on money flow line. I'm just going to touch on material and information flow line. So the at the very beginning, information flow line was here. And as time passed by, as improvements started taking place, the information flow line slowly started moving further inwards. It started moving as much as in it could move. And at a point, information flow line was the one which started triggering the material flow. So once the information goes in, then the material flow gets triggered. And as we all know that that's what is happening at the moment. So information flow line started playing a major role. And here is a extended supply chain that I'm showing over here. Like you have a manufacturer and he would have a set of major set of suppliers, and from him, or we call it as a tier one supplier, and from there it goes to tier two suppliers who are supplying the products, and I mean the components and all gets together combined as a single product, and then it moves to the distributors or the wholesalers. From there it goes to retailer levels of retailers, and finally it reaches the customer. So it's a bit of an expanded supply chain with the material and information flow line. So now we could see that when the manufacturing was happening in this way, it was more of a seller's market. The manufacturer had his own um, rule, or he had his own marketplace to play around, wherein whatever he produced, moved it to the customer end, and customers started picking the product from the outer end of the supply chain. So it was more of a seller's market. The examples that we can speak of seller's market is that is where we could find this particular model, the 800 model, was there in the market for more than 15 years. We had these bulk TVs, which was there in the market for more than 20 years. And if we take one of the mature products called paste, that was there in the market for more than 50, 70 years. So it was all all these products were there when the market was in a seller's market. But ideally, now that we know that it is no more a seller's market, because we could see the automotive industries, they keep uplifting their models once in every 4 years. And we know that electronics industry is bringing up with newer technologies, uh, 3D televisions, UHD televisions, or the TVs are changing once in every 6 months. You tend to find a new model coming out. And even with the paste, we could find clove flavor. I was surprised to see that Colgate has about 21 different types of flavors, or it has 21 varieties of its own in order to hold themselves in the market space. So this gives a clear idea that it is no more a seller's market. The market have made a shift, and where that market had got shifted, that is the question mark. So that is a market shift which is taking place. And what is the driving factor which is making this marketplace to go for a major shift? It is nothing but the information, because at the few minutes before, we saw that information is the one which starts triggering the material flow, and the idea is information need to go as much inside as it can, or information is striving to of itself, it is trying to go as much inside as it can. And this was made vigorous with the invent of internet. And with internet popping up, information started flooding inside, as much in depth as it can go. And this started changing the marketplace at a very wider range. The moment information started going in, immediately what we lost years before or decades before, which was the customization, slowly it started popping up. Wherein earlier it was mass customization, and from mass customization it moved to modular customization. Let me take you through an example how information started bringing the customer modular customization. But before that, the one thing that we all know is when it comes to supply chain, this is the sequence of stages how a supply chain goes. One is you have a supplier, you have a manufacturer, from manufacturer goes to a distributor, to retailer and customer. And this supply chain, not necessarily it should be in this sequence. It can go from stage to stage. Some products, it can directly go from manufacturer to retailer, from retailer to customer. Some products from manufacturer, it can directly go to the customer. Some it follows from supplier, manufacturer, retailer, and then to customer. So it keeps on changing from product to product. The idea, one thing that is clear is, though supply chain has its own stages, but not necessary or not always a product would follow the same sequence. The sequence differ from product to product. Let us go have a look at a product wherein um, we could see, if I say that there is a customer who is involved in assembling the product, um, like like people would most of the time I hear from people, no, I have never seen or I have not seen an issue where there is a customer who is directly involved in assembling a product. Because I tend to ask a question: can you name one example wherein a customer comes in terms of assembling his own product? And if we take 1,000 customers, there are 1,000 customers who come with 1,000 different options of his product. And if I ask them to name that, people tend to say like, no, that is not happening. But in reality, that started to happen before 10 years itself. Let me take through a case example. Like if you want to go for a purchase of a computer, and ideally, when we go for purchase of a computer, we have 5 different criteria in our mind. Or I just picked up the very generalized one, what most people tend to go for. One is the spec, like what is the hard disk that they are looking at, what is the graphics card that they are looking at, or what is the RAM that they are looking at, and the price, the budget that they have fixed, and what is the design that they are looking at. Some people would like to have a lightweight, a 14-inch laptop. Some people would say that for me a wider screen is better, so 17-inch laptop. So it depends from person to person. So the design becomes one of the criteria, and some people stick to certain brands, and we have our own notion on the brand, and we also decide how better is the service. So these would be the generic 5 criteria that we take beforehand before we go for a purchase of a computer. So when we go in with this particular spec, and when we go to a shop, we find so many computers over there. Some way or other, we tend to make a compromise. Let's say, for example, for me, I need a higher graphics card. A medium memory is fine. Maybe 500 GB is fine with me. But for me, the size of the laptop is very much essential. I need a 14-inch screen, but somewhere or other, I need to make a compromise that they would say that 1 TB is the hardest that is available. Graphics card, no, I could get only a certain spec. If I need to go for a higher graphics card, I need to go for a larger screen or a bulkier laptop. So I need to make a compromise at one point or other, even for the simple process of buying a laptop. This is from the manufacturer perspective. I mean, this is from the customer perspective. But from the manufacturer perspective, it is hard for a manufacturer to keep uh, different varieties of same laptop lined up in a store, because the inventory, the cost, everything goes up. And inventory is a major thing which goes up. And the moment the inventory goes up, we all know that the price of a product also goes up, or that becomes a threat to the entire manufacturing supply chain system itself. Under this circumstance, Dell came out with an idea that you can, using information sitting at home, you can completely assemble your entire product, and then the product would be delivered back to you to your home. So what happens is you pick the, get into the site, you look at the various online options, you decide how you want your assembly to, and then you can even decide when you want your product to be delivered and how you want your product to be delivered. A case example is you get into the Dell website, so you pick what is the size of screen that you're looking at. So it gives you an options of laptop, and once you choose your screen, then you can go for an option of selecting your process speed, pick your memory, pick your hard drive size, decide what you want. So this completely gives up an option of customizing. What we are doing is, here we are completely customizing the product for our own requirement. And then we can even select the processor speed that we are looking at, choose your operating system, and even go for installation of your security software, whichever you feel comfortable. And then you pick and choose when you want your product to be delivered. And even in that, you can also, now that the system permits you to decide, let's say that I want my product to be delivered on Sunday morning between 11 to 12. Yes, even that is possible in current scenario. So to that extent, the entire product line have changed, and you can also keep a track of what is happening and where your product is reaching. So what Dell have did over here is, ideally Dell went for a option of mass customization. Let's say that Dell gets its product from three different people. Hard disk from one person, screen from other person, processor from other person. So the moment this customer orders it online, then only Dell tends to place the order for all these suppliers. So once the suppliers get their order, they tend to deliver these products to the assembly plant of Dell. And once all these things arrive to that assembly plant, product gets assembled and then it is directly delivered to the customer. So what is happening over here is, here the customer is not making any compromise. He gets to choose what the product he is looking for. On other hand, for the manufacturer also, earlier Dell used to hold an inventory in crores or in millions of dollars. Now Dell's inventory came down to hours. The maximum inventory that Dell holds is roughly about um, less than a quarter of $1 million. And on top of it, it only holds the inventory for a time period of 4 hours. Dell never holds an inventory of more than 4 hours. So with the information moving in inside the supply chain, the entire scenario have changed. What have happened is the mass produced products are completely customized, or we call it as modular customization. It is assembled according to the customer need and it was delivered. So here there is a balance which have happened between both the manufacturer and the customer. Manufacturer had his compromise and customer also got his compromise, or both got in a way of benefit. There are some industries which started enjoying this benefit, like if we, another case example that we can think of is paint shops. Like no paint shop holds an inventory as what they were holding in early days. Like you go and give your color code, in a matter of 15 to 20 minutes your product is delivered. The warehouses of paint shops, which were in thousands of square feet, now came to less than thousand of square feet. So now no more bulkier paint shops that are seen here. It is yet another example where both the customer enjoyed, both the man and the manufacturer also enjoyed his his stand. So all these things gives a very clear idea that it is no more a seller's market. The marketplace have got completely transformed. Earlier, the information tend to stay at the very outer end or at the retailer end. The customer demand stops here. But now the customer demand, what we have seen through the example of Dell, or what we spoke about the paint as an example, we could see that information have gone until to the end of manufacturing. And once the information triggers, then only the material flow line starts, and then that is the point where the manufacturing started taking place and the product got delivered. So it is very much clear that the information started driving things in a supply chain in a very different perspective, and this led to a situation that it is no more seller's market, it is a buyer's market, and it is the customer who started demanding, and the situation is the manufacturers are forced to meet the customer needs. So when such a situation is happening, the older technology or the subtractive manufacturing technology, it is hard for the subtractive manufacturing technology to withstand the pressure that it is getting, because if you take 1,000 customers, 1,000 customers will start demanding 1,000 different types of products, and it is not easy to satisfy everyone. Or the traditional subtractive manufacturing system can't make a balance; it has its own limitations. So, and though we went for automation, and still it has its own pressure, and it is not easy to withstand that. This is where people started speaking of the moment they started understanding that it is no more a seller's market, it is more of a buyer's market, and this buyer's market is driven by information as a entity. So people started realizing this, and it is as the floor is open for the customer to demand for his own product. This gave a new perspective, or it gave a very clear idea that the entire marketplace is shifting towards the future, and the future is Industry 4.0. So that is where people started speaking about Industry 4.0, and we all know that Industry 4.0 is nothing but more of an information driven. And in terms of manufacturing perspective, all it have happened is it started to close the cycle in terms of manufacturing, wherein the traditional highly skilled labor who was able to customize products is being replaced by a newer technology, which is nothing but the additive manufacturing technology, what they are speaking at a very wider range. So that is why you would find Industry 4.0 carries additive manufacturing as one of the major entity among the seven different entities. So, what is additive manufacturing? So, this idea of additive manufacturing, earlier it comes with many names, or this technology was ideally invented as a replacement to prototyping, because they got fed up with clay-based prototyping, thermocol prototyping, or wooden-based prototyping, because it was taking its own time, and that is the period that they wanted to have make the prototyping at a faster rate. And when they wanted to make the prototyping at a faster rate, they needed a better technology, and that is where they it was coined as rapid prototyping. So when rapid prototyping came into existence, this happened somewhere in 2001. Airbus was suddenly in need of a quantity of 200 nozzles, which they want to place in their flight. And they realized that they forgot to, somewhere they missed the paperwork, and they couldn't produce, um, they forgot to produce the die for that particular Avent knobs. And the demand was for 400 units of those, and now they don't have time to produce those 400 units of those. And that is why for the first time they thought, can we use rapid prototyping, because anyways it's a plastic component, and they could make the drawing, and once they can make the drawing, they know that they can print it in a rapid prototyping machine. So Airbus went for this technology for the first time, and they bulk produced 400 units of those. Rather going for an injection molding, they produced in rapid prototyping machines. So this made an entire change in the scenario. That was the time period when rapid prototyping was called as rapid manufacturing, and later on people called it as 3D printing, because people saw it as more like a 2D printer. But only thing is, it started printing products in the third dimension as well, so they called it as 3D printing. And then came various technologies which started popping up in rapid prototyping, or the early rapid prototyping. And now the same thing, with many technologies popping up every day, and then many technologies are popping up in that area, and many material improvements are happening. And that was the timeline that they called it as additive manufacturing, wherein the terminology, additive manufacturing primarily came into existence because we were calling the traditional manufacturing as subtractive manufacturing. So then, because of the final end product, so they called it as additive manufacturing. So the idea behind additive manufacturing is it is more like the injection molding technique. You just pour the bulk of a material in the cavity, but here you put the same idea, but you put the material in a defined space and add layer over layer in that defined space, and you get your product built. So that is nothing but that was the idea behind additive manufacturing technology. Let us say that we want to build this particular product, and we know that there are some you can't spread the material over here. Obviously it will fall off. So this gave the requirement of introducing two nozzles. One is the actual material, or it is for supplying the model material, and the other one is to support for the support material. So how it happens is, when the first layer prints with the model material, and when it is done, wherever you need the model material, the first nozzle or the model material nozzle delivers the actual material. And once it is done, the entire the rapid prototyping or the additive manufacturing system knows that in future it is going to print a component on top, or something on top. So what it does is it uses the support nozzle, and the support material is printed over here. So you could see this dark gray one is the support material which gets printed, and then comes the light gray one where the actual material is printed. So then the product gets built layer over layer. So once the product is built, then taking out from the table, the support structures are being removed, and you tend to get this final end product for application. So this is the entire idea behind additive manufacturing, wherein you keep adding layer to layer and then you produce your end product. Like all of the mission sequence, like if we take a lathe, we need to go for holding the raw material, and then we need to center it or make sure it is centered properly, and then we go for clamping, and then we go for tooling operation. In the same manner, as we follow a particular sequence for each and every machine, like hobbing or like a planner, each have its own sequence. In the same manner, additive manufacturing also has its sequence, but the only difference is no matter whatever be the type of machine, mostly the sequence of operation for additive manufacturing tend to remain the same. It would slightly change during the pre-processing stage and the post-processing stage. Those are the two times where there would be a slight change which would occur. And this change is not a major deviant. The change occurs somewhere between 60 to 35% is the deviation which tend to take place during pre or post processing, and rest of it always remains the same. Here, let us say that whatever you give as an input, it is converted into a common language, wherein you call it as surface distillation language. This is the language which is generally used in all the additive manufacturing machines. And once you give the design in an STL format, then it goes for a pre-processing stage, wherein you decide how you want to put your product in the machine table, like whether you want to build your product in a vertical manner, in an inclined manner, or which is the position that you're looking at manufacturing your product. Based on that, your pre-processing changes, and once in this pre-processing stage, it tends to develop the support structures. And once the support structure is done, so here you tend to get the actual material requirement. Here you tend to decide on the support material requirement, and this actual and support material combines together and comes as a file transfer process, wherein each slice comes in and the build process starts taking place. Once the build process is done, depending on the type of machining or type of additive manufacturing machine that you use, the post processing changes. And it is more or less an expanded idea of the stages. Like you give your input, then it goes as a tessellation language, and that is where you tend to slice it up, and you put it into an RP system or an additive manufacturing system where the part is built. And once the part is built, you take it for post processing. Sometimes you break the support structures, you for the additive manufacture part. And once you're done with that, then you tend to take your final end product and you take it for application. Here in this process, I have given a particular emphasis on the inputs because when it comes to additive manufacturing, now it came to a stage that earlier, when it comes to manufacturing, there were some production constraints. Understanding the production constraints, that is where we came out with a couple of terminologies called design for manufacturer, design for assembly. All these terminologies came up. The reason is you had certain limitations in manufacturing, but now the entire scenario got changed. Now the you can manufacture, but that was not the case earlier. Whatever you want to manufacture, still you can't manufacture. You need to change it according to the manufacturing requirements. But now it is completely a reversal situation. What you can imagine, you can manufacture. So the limitation stops in imagination. So that is why I wanted to give a bit of an emphasis on inputs that we can give into rapid prototyping or the so-called additive manufacturing system. Anything that you give it as a 2D or 3D drawing, it can be taken up. So people were pretty much comfortable in giving 2D and 3D drawings, and that is the period that they thought that can I use a CMM, get the data from there, and can I do a reverse engineering process? Because now that I have a die which is worn out, but I don't have the dimensions of the die at the moment immediately. So let me put it under a CMM, probe it, and from the cloud point data, I can fine tune the dimensions and I can still manufacture it through an additive manufacturing. So that was made possible. And users of CMM, they very well know that CMM can't be used when it comes to intricate profiles. So that is where the idea came out with Faro came out with an option of non-contact measuring or using laser beams in order to measure. Again, that falls a deviation whether you're using a white light or blue light scanner. And using a non-contact measuring, now you are able to get very intricate parts which was missing earlier. And once you tend to get the intricate parts, you can also go for intricacy in terms of size or in terms of complexity or in terms of hidden values as well. So you can pick it from there, and from the various scanners you can pick the data from there, and you can still go for printing it directly in one of the additive manufacturing machines. The idea doesn't stop there. It also moved to the level of taking the data from MRI or CT scan, wherein you can get the data in DICOM files, and from DICOM you can convert it into an STL file, which could be manufactured using an additive manufacturing system. So when we need to understand all the intricate requirements, like if I only need a bone data, then I would go for a CT scan data. But if I need, along with bone, I need to do some fine tuning in the flesh or in the nerves, then I would go for an MRI data, and from there I would tend to pick it from there, and I would go for producing the final end part of the requirement. And it doesn't stop there. As I mentioned, imagination is the one that limits. So that is where geomagic hapticom came into existence, wherein we know that we can't draw the profile of a hand, or we can't draw something of very complex or very inclined profiles or the B splines, which is possible, which is not at all easy in any other manufacturing, any other drawing tools, because much of our drawing tools can focus only on lines and curves, or mostly on terms of lines. But when it comes to complicated curves, it won't be in a position to support it. So that is why Hapticom came into existence, wherein you can draw the profiles, very intricate profiles, which was not possible earlier. And those could be given as an input for an additive manufacturing system. So in concise, an additive manufacturing can take the data from 3D CAD, 2D CAD, point of cloud data from the CMM, and also from any of the diagnostic tools like MRI or CT scan data. All this could be given as an input for a 3D printing system, and the part could be printed over there. One very important thing is, like, most of the people think that okay, I have a additive manufacturing system, now I don't need to bother, and the system can by itself it can produce a part. But that is not the reality. The reality is how you are expecting a skilled labor in terms of operating a traditional subtractive machine. The same type of skilled labor is essential for an additive manufacturing system also. The reason is, you can print a part, and the way you print a part, it would change the entire scenario. Let me take you through this particular example. This is a plastic part that need to be printed. I can print this part by putting it horizontally on the machine table, or I can put it inclinely on the machine table. And depending on the type, how I orient this part, it is going to change, or it is going to take the amount of time, or it is also going to consume the raw material in different phase. Like, let us say that I mean, if I'm going to put it horizontal, it is going to take around 20, 29 minutes for the part to get completed. The same thing, if I put it vertical, it is going to take 1 hour 49 minutes. Same part, no change. I'm putting it completely on the height wise, wherein I'm going for a higher Z axis. So that means that it is going to take 3 hours, and the amount of support material, the grinding support material is going to take 3 hours. While printing also, it is going to take 3 hours. While cleaning also, it is going to take 3 hours. Whereas in this case, the actual material quantity is not going to change, but the raw material, the support material quantity is going to change based on the orientation. Not only it gets stopped over here, it also plays in terms of how the quality of the print of the part that you're going to get. The best quality, again, you need to decide what is the quality that you are expecting out of an 3D printing system. So you need to specify, you need to give a clear understanding of what is the quality that you're expecting out of your print. So based on the quality, you need to orient this part, because based on this orientation only, your time is going to change, your material consumption is going to change. Most of the people, they don't tend to make a note of it. They think that additive manufacturing, once if we have it, it can do everything, and it will give the part at a reduced lead time. No, that is not a fact. It again, it needs a skilled labor, a skilled person who can understand it. What is the orientation? What is the best orientation they can do? What is the best combination of material that they can take out with? So all those are quite essential, even when it comes to additive manufacturing. So this is the part that is printed in an FDM. You could see that we oriented it in a horizontal manner, because that is the best orientation which we wanted to have. And the support structure was just removed off, as it is a breakaway support structure. So when we are printing any complex part, it doesn't stop over there just by printing. It also takes time in terms of post processing. So we need to take much of a care in terms of undergoing this post processing when it comes to additive manufacturing. It doesn't stop there. So with a slight idea on that, we'll have a slight look on the additive manufacturing process, and then we'll see where we can integrate additive and supply chain together. So if we take additive manufacturing process, it broadly classifies into two types. One is the material first approach and the process first approach. When it goes to material first approach, you have the type of material. You need to choose the machine based on the material that you're going for. Are you going for metal? Earlier, there was an option of metals and plastics, but now the division goes on as metals and non-metals, because now you can even print rubber-like parts using an additive manufacturing system. So either you can print pure metals, or you can print non-metals. That is, you can change the show hardness of a particular part, and you can start printing it. When it comes to, that is the advantage of non-metals. When it comes to metals, No more, you don't need to have the bulkier products, or you don't need to think of design for assembly or design for manufacture. Here, whatever you think, whatever your analysis package says, that is the best option for reduced material consumption, optimum load withstanding abilities, or optimum thermal resistance. Whatever your analysis software says that it is the best option to go for, you can straight away go for that particular option in a metal additive printing. But if you're going for a metal additive printing, and if you're still going to um, have a traditional engineering styled um, process, then it is not an option to go for it. Here I have shown two different case examples, wherein in a metal additive process, you could see that a complete bulk material has been removed, and only the structural rigidity has been provided over here. It can withstand the varying loads. On other hand, here also we can see that for this particular component, they wanted to have an improved thermal dispersion. So that is why they went for this particular design. It never compromised. But one thing when it comes to metals is we need to make sure whether we are removing off the thermal stresses once the product is produced. Because still now, when it comes to additive manufacturing of metal parts, we need to have a complete understanding on the process, and then only we need to take that particular product for application. Because if we mismatch the process and the product, metal additive manufacturing is one of the dangerous areas that we can touch in terms of additive manufacturing. So moving to plastics, or I wouldn't say it as plastics, moving to non-metals. um, like ideally it goes in terms of classification, goes in terms of the type of raw material that you are going to use. Are you going to use it as a solid one, or are you going to use it as a paste form, or is it the raw material going to be a liquid form or a gaseous form? At the moment, much of the gaseous additive manufacturing technologies have been completely removed. It is more of a solid, liquid, or semi-solid base. So among this, I would only touch on, I would quickly touch on the different types. The first very renowned type is called as a stereolithography, or it is otherwise called as SLA process. The idea of stereolithography came from the idea of Polaroid cameras, wherein you take a picture, it's a 2D picture, you expose it to UV light, and the moment you expose it, you shake it off, and you tend to get your final end product, or the photo is there. So looking at this, people thought that if I'm able to make a 2D picture immediately, why can't I make a 3D picture? So that is where stereolithography came into existence. It uses the idea of a polymeric liquid was used, and the entire product is built in this liquid bed. To start with, the bed or the machine table lies at the top, and it has multiple pores on top of it. And as we had seen through the stages of additive manufacturing, you gave your product data, and your product data has been sliced in layers. At the very beginning, this is a flower vase that they wanted to print, and this one single layer is the one that they wanted to print. So the laser only burns or heats the raw material only where it need to be built. So as it heats, the photovoltaic resin or polymeric resin, the photosensitive resin with a UV laser, it tends to get hardened, and you tend to have your part which got built. So here you can see layers have been built over there. And once those layers are built, the machine table moves down, and the liquid resin comes to the top. And as the process keeps on repeating, the table keeps moving down for every slice, and the liquid material comes up for every slice, and the part is built in this manner. I have a short video which describes how it is done.
Motorola Product Testing Services offers rapid prototyping utilizing state-of-the-art stereolithography technology. The prototyping process begins with the conversion of our customer's three-dimensional CAD drawing into a file that is exclusively used for the rapid prototyping procedure. The part is virtually positioned in order to obtain optimal quality, accuracy, and fine detail preservation. Special software prepares the file for a prototype build by converting the design into thin cross sections that map out the solid regions of the part. When downloaded, the output file guides an ultraviolet laser beam and scans a specified cross section on the surface of the liquid photopolymer resin. A platform attached to an elevator assembly is used as the foundation for the prototypes and incrementally indexes the platform into a vat of resin. Once the liquid photopolymer resin is exposed to the laser, it solidifies into an epoxy-like plastic material. The process is continued layer by layer, cross-section after cross-section until the part is complete. Once the building procedure is complete, the prototype part is removed and processed through a solvent rinsing system to remove residual and uncured resin. The part is then cured by placing it in an ultraviolet post-curing apparatus. After finalizing the curing process, the part is ready for hand finishing, sanding, bead blasting, and painting, dependent on the intended use of the prototype as specified by our customer. With 10 years of experience, our rapid prototyping team has the skills and resources to provide our customers with accurate and professionally refined prototype parts that can be utilized for design verification or tooling aids, analyzed for fit, form, and function, or exhibited for promotional purposes. Contact us to quote your next rapid
So we saw a bit of stereolithography apparatus. And one thing is, let us say that you are looking for a very transparent part or a glass-like product, or more or less like a polycarbonate or an acrylic type of part. Stereolithography is one apparatus which you can think of. And when it comes to the situation like, no, I don't need a very transparent part, but my part is very complex one, and it has very fine curves in it, and I want to directly take it for application and testing. Or in other words, let's say that you have a very complex profiled impeller, and you want to produce that particular impeller, and you want to test that impeller. Under that circumstance, the immediate option that you can think of as a selective laser sintering, wherein in terms of selective laser sintering, it's a powder-based product process, and here it uses a particle of size of 20 to 100 microns in diameter, and it uses polymeric or thermoplastic powders, and from here the part is built. And SLS is one technology wherein when it comes to metals, you can use metals like stainless steel, zinc, titanium, bronze, various grades of tool steel, all could be produced when it comes to SLS based printing process. So the idea behind the SLS printing processes, in earlier stage, we saw the liquid coming up, but here a powder bed is stretched. And as the powder bed is stretched, according to the profile or according to the requirement, a laser in that manner. Here you could see that a delivery piston delivers the powder, and a leveling roller takes the raw material which has been distributed, and it runs over the fabricating space. And in this fabricating space, the leveling roller moves or spreads over the raw material. And once the raw material is spreaded up, the leveling roller stays here, and then the laser burns the region where the part need to be built. Once the build process is done, the entire fabrication piston moves down by one slice. As it moves down by one slice, this roller which is present here, it goes to process gets repeated. And this was the very early system which was designed. People realized that yes, the idea behind additive manufacturing is to speeden up the process, and they realized that because of this one delivery piston, the entire system is stopping for some time, and that is where they came out with the idea that of two pistons. For the first time, this piston moves up, and the roller moves the raw material to this fabricating space. and it comes entirely to this end. And once this is done, the process is built or the product is built over here. This delivery piston will deliver or move up by a slice, and the roller which is present here, it tends to deliver the material here and it moves to this end. So by this continuous process, the part is built. And one major advantage is, like here, you don't need to remove you don't need to have the support structures at all, because your entire part lies on the raw material itself. Like if it is a very complex part, here the actual material itself will perform the job of a support structure. So that means that here it doesn't matter if you're concerned about the type or the strength of the part, and the circumstance permits you to build your part in a higher Z axis, you don't need to bother for the support material conception, because your actual material itself is used as a support material. I have a short video which describes how it is done. These are the two delivery piston sides. So here you could see the delivery piston, one of the delivery piston moved up, and the leveling roller moved the material. And as the laser light blows, the part is built. Once the part is built, the leveling roller again spreads over the material and moves to the other end. Once the entire process is done, you move the table up, the entire part along with the support material comes out. You take the entire part out. Your actual component is surrounded by the raw material. So you just remove off the raw material, and we can reuse the raw material in a proportion of 80-20. That is, 20 parts is going to be the new raw material and 80 parts is the old raw material. And one best thing about this particular SLS process is you can build any complex profile parts, and you can directly take it for application. You don't need to do anything further to that. You can directly take it for application. um, any complex profiles, this gives an idea that your imagination is the limitation. Like anything that you can imagine, you can build this particular part over by using an selective laser sintering process. One of the typical example is like an architect before spending some crores of money on a building. mm, If he wants to, this is one of the very complex structure which can't be built by any other uh, 3D printing or any other additive manufacturing technology. So SLS is only one option wherein um, you can print this. No complexity goes off, everything stays in line. The next one is the very widely used FDM technology, or fused deposition modeling technique, which is developed in Arizona. And the idea behind this, you slightly heat the material to 0.5 degrees centigrade, and as it touches the melting temperature, you extrude that particular part. So here you can use products which are suitable for medical grade plastics. You can use fire retardant plastics, or you can use ABS, elastomers. All those could be possible. So you have two rollers. One is the support material, and the other one is the actual material. And here you could see that the blue one is the actual part, and while the light blue one is the support structure. Here is a description of how FDM works.
You can build durable, accurate, simply sending files right from your desktop or over your network. Strong and functional parts are built from your 3D CAD files using patented Stratasys fused deposition modeling technology. Powerful Insight pre-processing software imports STL files and automatically slices the part, generating the necessary support structures and extrusion paths. maximizing build efficiency while minimizing user involvement. Inside the system's heated build envelope, model material in filament form is heated to a less viscous state for extrusion. The model is built layer by layer from the bottom up. On each layer, the extrusion tip follows a precise plastic modeling material, along with any necessary support structures. When applicable, Waterworks provides the final step, enabling complex geometries and fully functional assemblies in a single build. Soluble supports are simply dissolved in a water-based solution, resulting in a part with smooth surface finish and fine details intact.
So here we have seen a case of a fused deposition modeling. So among the types, it is one of the very cheaper technique to go for. And here are some of the examples, um, products that could be manufactured using this. Um, and all we have seen is either transparent part or a white color ABS part. But what if the situation is if you want to have color parts for visual communication, for sharing the idea of a component with one of the suppliers? Under that circumstance, 3D printing is one of the option, wherein it uses multiple colors in order to build a part. Here you can design a part. Once after designing a part, you can pick and choose the colors that you want to orient for it, and then you can print the part. The idea of printing is like as what we have seen in the earlier case, the powder gets spreaded, and wherever you need to bind it, or rather using an UV light, here it tends to sprinkle a binder material. And this binder material, it is the one which binds the earlier layer with the current layer, and it starts getting binded layer over layer. And once the binding have happened, then you tend to get the final end part. So it is more of a binding of layer, one layer with the other layer. And mostly what people tend to do is, ZCorp did at the very beginning is, it tend to define the color code with the binder. So wherever you need a different color, the binder gets color infused. And based on that, you tend to get the particular color for each and every layer. And by that way, the part is produced. So here is an example of certain 3D printing part, how the part is being printed using one of the 3D printing labs.
3D models are easily and affordably delivered. The Z Printer 450 brings CAD files to life as realistic physical 3D models with precise details and brilliant color, and does so 5 to 10 times faster than other systems at less than half the cost. Dramatically present the proposed look, feel, and style of product designs and prototypes, vividly display architectural visions, and better communicate 3D information in education, healthcare, and the arts, all in ways that electronic displays cannot. The first automated 3D printer, the Z Printer 450, is remarkably easy to use and very office-friendly, with clean, quiet operation. Come and see for yourself at ThingLab's Central London demonstration studio. The Z Printer 450 is for those seeking high-quality color models, with the convenience of an in-house printer to build those models anytime, anywhere. The uniquely automated Z Printer 450 simplifies the entire 3D printing process. Self-contained and self-monitoring, it manages nearly every aspect of printing. Simply import your 3D data file into the Z-Print software, position as desired, and follow the prompts. The system automatically checks supplies and printer readiness, ensuring you always have the right amount of materials to complete the job. If supplies need replenishing, it's as easy as inserting a 1 litre binder cartridge and connecting. When ready, click 3D Print and watch your 3D model emerge from the bottom up, one cross-section at a time. In 450 DPI resolution, advanced inkjet technology builds models 5 to 10 times faster than any other rapid prototype systems. So you get your model in hours, not days. When printing is complete, a vacuum and motion system automatically removes up to 80% of loose powder and recycles it for future use. Removing the remaining powder is just as easy, using lightly compressed air in an enclosed chamber that vacuums away particles as usual. Plus, no physical support structures attached to the model, like in some other parts. There's no scraping tools or chemical paints. Every 3D model is clean and ready for finishing. Choose a quick dip in Z-Bond sealant, followed by a short drying period. Get the same effect by dripping Z-Bond over the model, or lightly brush with Z-Max infiltrant for a strong, brilliant color finish. So which you choose, you get a smooth, vivid color model that lasts, and you get it fast. In fact, from start to finish, this model was printed, powdered, and finished in under 4 hours. The Z-Printer 450 is incredibly office-friendly, with a small footprint, negative pressure dust control, noise suppression, and zero liquid waste. It's just like any other printer in your office. Everyone can afford to create 3D concept models, functional product prototypes, architectural models, and more, and do it all in-house.
So when it comes to 3D printing, like if you're only looking for an option of a knowledge sharing process, or you just want to see the prototypes before application, or you want to discuss about your product to your vendors, 3D printing is the right option. Here, any part that you print using the 3D printer, you can directly take it for application, because by the way how it is manufactured, it doesn't provide the right strength. So the product tends to fail during application. So we have seen the very widely used technology, and then people thought that okay, I wanted to make a core for my foundry, and I am looking for a possible machine for that. Yes, one of the options that is available is layer laminated manufacturing, or otherwise it is called as LOM. So the idea behind LOM is you tend to supply the raw material in a sheet form, and this raw material at the base it has a glue, and or we can say that it's one-sided, more like sellotape, wherein it is glued on one of its side, and it gets spreaded up, and once it is spreaded up, a leveling roller or a laminating roller will slide over to remove of any possible air bubbles that would arrive. And as it moves on, there comes a 25 to 40-watt laser. That particular laser burns only the region where you want your product to be built, and rest of it, it tends to you call it as decubing, or it tends to develop cube-like structures, so that it is easy to remove the actual component and the support structures once the part is built. So for that, it tends to produce cube-like structures. Here you can see the ring-like structure is the actual component that they want, whereas a cube-like structure is parallelly produced. This is produced in such a way that the ring could be taken off, removed off easily once the process is done. And anything that is done for the second layer, the take-up roll rolls up the extra material, and while the material supply roll would start feeding the newer set of material. So by this process, laminated object manufacturing tends to produce part layer over layer, and it is suitable for an application wherein you wanted to produce parts like a core for your foundry. So that is a place where you can use it. So anything that you produce, you can use LOM as an application where you can do that particular process. And now moving to a technology called polyjet technology, wherein if you want to produce a transparent part, we can only produce by stereolithography. If you want to produce complex part, until now SLS is only one option. And if you want to produce colorful parts, 3D printing is the only option. But polyjet, I would say that polyjet gives a combination of all these three technologies together in one single technique, which is the polyjet printing technology. It has about 8 different print heads, wherein four is for delivery of support material and four is for delivery of model material. And here the material is distributed in a form of droplets, while the material is delivered in terms of droplet. Once it is delivered according to the layers where it need to be produced, and UV light passes on, and it tends to harden the resin. And once that is done, the next layer starts up. Here I have shown one example wherein um, if you want to produce an ABS part, that is possible. I want to produce a polycarbonate part, a glass-like structure, that is also possible. And I also wanted to produce rubber keys, that is also possible. So all these three things are possible in this particular technology, wherein in earlier case, if I want to produce a polycarbonate or an acrylic based part, I need to go for an stereolithography. This I need to use an SLS or an FDM. And this I need to go for, I can't do it in earlier technologies. So I need to, because earlier technologies doesn't permit to print rubber like parts. Whereas in polyjet technology, it is possible to print the rubber like parts as well. And when I say that, all these three different materials can be printed in one single go itself. On top of it, I can also change the show hardness level. Like we know that the show hardness 100 is a very hard one. Show hardness 20 is quite flexible one. So for one single part, I can decide like I need this part to be, let's say for example, I need this part to be show hardness of 20. I need this to be of 40. I need this part to be built at show hardness 60, and I need this to be of show hardness of 100. It is possible to manufacture using this polyjet technology, wherein we can keep changing the show hardness and still we can build a part. So ideally, this particular technology, using this, we can print 148 different combinations of materials. And this is the place where we can use digital materials as well. We can combine different materials, different combinations of colors. Everything is possible using this technology. And it was said that even Google Glass was, which they used during virtual operations or during real-time operations. This technology was used. Here it uses three different types of material. One is the primary material and the secondary material. The primary material tend to be a dominant one. Secondary would be a flexible one, and I can also go for a digital material wherein if I want to change the show hardness of the material from time to time, I can do that using this particular technology. So here we have seen a case wherein we can print all these combinations, and very importantly, you could see a brush-like structure is printed over here. That is a rubber and a plastic one has been made. In traditional manufacturing, we would end up gluing it up together or giving some notches for fixing these two. But now you can manufacture these two combinations together in one single go, which is very widely used. These applications are very widely used in pump industries or in textile industries, wherein they wanted to hold both the combinations of plastics and rubber going together. That is where this particular technology is widely seen applied over there. Right. Moving back to the objectives of webinar, now that we have seen what additive manufacturing is, where supply chain is, where these two stand separate, now we touch on the objectives of the webinar. That is customer involved product manufacturing, how we can reduce the inventory and lead time on custom products. I'll take you through some of the examples. Like when it comes to the integration of supply chain and additive manufacturing, or the early names of rapid prototyping, rapid manufacturing, 3D printing. When it comes to these two integration, this you need to decide what is that you want to achieve through that integration. That is the very crucial fact to start with. Here, I have shown this integration application, like wherein I wanted to produce very customized products. I wanted to bring the customer as much inside the supply chain as I can. I want to produce the product completely focused on the customer. And my requirement is I am going to produce the products which are very complex in nature and which can't be produced by traditional manufacturing systems. And though I am going to produce products which are very complex, I'm looking for something like a very high accurate part. And I like once we have a very complex profile, and if we start speaking of high accurate part, obviously it is going to consume more amount of lead time. It doesn't matter whether it is manufacturing lead time or logistics. I want to shrink the entire lead time, which is a combination of both supply chain lead time and the lead time on manufacturing. So this is where I'm looking at. I want to reduce the lead time of the entire process. So that is where I wanted to use additive manufacturing. On other hand, by bringing in the supply chain, I want to bring down the inventory. I want to reduce the cost of the product. Again, I want to go for lead time reduction over here. And I want to be as lean as I can in my entire supply chain process. I don't want to have many number of players in my supply chain. And I will want to cut off all the possible waste that it can occur. And I want to be very agile in my system. So these are my criteria that I'm considering in terms of supply chain perspective and in terms of additive manufacturing perspective, and I'm trying to integrate. So when we integrate these two, there are many areas that we can look at. Like we can look in terms of aerospace, we can look in terms of foundries, we can look in terms of pump industry or any other production industry. Like here I have taken some case examples through healthcare, because at the moment I felt going through sharing some live examples would show how essentially it is playing its own role. So this integration I have shown through healthcare as a product application. So here, starting with the first case study, like here it is going to be a completely a customer involved product manufacturing, and I'm going to go for co-customization. If I'm speaking of 100 customers, I'm going to produce 100 different products. No product is very same to the next customer. All are going to be 100 different products. And that means that the variety is very high and the volume is very low. So one customer, one product, but for 100 customers, I'm going for 100 different types of products. That's what I'm speaking about. And at the moment, the current lead time is 48 hours. You get the product, but again, the correction time or fine tuning time takes quite a longer time. In theoretically, or actually now it tends to take more than 15 days for a customer to get his final end product, which gives a perfect fit for him. Whereas in this technology, we have shown that we can deliver the product in a matter of 4 to 6 hours, and the customer leaves out with 100% satisfaction. What is the product that we are speaking of here? Here it is the product on dental aligners. Like we all know that mm, when the situation is like this, we need to align our dental tooth. So that is why we took this particular case study. Like in terms of dentistry, one very important thing is, like any other manufacturing method, the reason why I wanted to touch healthcare now is because so this gives a very clear idea. The moment we are able to do it here, it shouldn't be an issue to do it in actual manufacturing scenario, because in terms of dentistry, they want to align this tooth. And when it comes to aligning this tooth, a dentist, he want to move this tooth to a degree, he want it is inclined at a certain degree. He want to move this to 35 degrees. Let's say, for example, this tooth need to be moved back by 35 degrees, and this tooth need to be rotated by another 8 degrees so that it gets aligned to this. Okay. My requirement is this tooth need to be moved back by 35 degrees, or it will need to go back by minus 35 degrees, and this need to be rotated by 7 degrees. The very interesting thing is, yes, I know that I need to change these variations, but there is no measure to measure this degree. There is no tool in the world that is available wherein I can put it on the face and I can say that I can turn this tooth to 35 degrees and I can rotate this tooth by 7 degrees. It is not possible because there is no measure, no measuring device, no calibration device which is available in order to do this measurement. It all goes by, even now, in spite of all the accurate measurement tools that we have for production application, it all goes by um, virtual thoughts. A maxillofacial surgeon decides like, yes, now it has got realigned. That's all he does. It is completely done by eyesight approximation. There is no measuring tool. So let's see how it is done. So at the current practice, like in order to do this, what they do is they tend to take a mold, and in order of taking the mold, uh, for taking a mold, and in order to move this back, first they would take these three tooth as a reference, because these three are aligned properly. And taking these three as a reference, they will start rotating this and they will start moving this backwards. So once that is done, then they go for, once these two tooths are corrected, then they take these three teeth as a reference and then they tend to orient this tooth. And then taking these four, then they would go for orienting this fourth one. So what we are speaking about here is, oh, one is corrected, or that is why it goes in stages. One, they are done with the first stage, then they go for orienting the second stage. If we think about for a bit, and we all know that dental aligners, or it is otherwise it is the braces that we use, is the only technology that is available. And even when we have a small chewing gum in our mouth, we know how difficult it is to have or take our own food, because it is not something easy. In that case, you can imagine a situation what people go through when they have some aligners which are placed in their mouth for a continuous 15 days, or the metal braces which lies inside their mouth for continuous 15 days. Once in 15 days, they tend to tighten the metal braces and they tend to realign it as stage by stage. So then we try to see when these aligners, these dental braces were invented, and it all goes back to 1700s. From 1700s till now, only difference that have happened is they have changed, improved from the traditional method. This was the French method, wherein they tend to put the drill in the tooth and then they try to align the tooth. And from here, we have moved to here. But still, it is not the one that gives a comfort to a patient. Again, in spite of comfort, there is no accurate way that it is done. So it is still done in a very traditional manner. And even then, when they tend to do this using these metal braces, people who wear metal braces There is a highest amount of data which shows that they tend to have more amount of cavities because it is not easy to clean the tooth while wearing these metal braces, and there were situations wherein while tightening the tooth tends to get broken off. So these were some of the practical problems that it tends to occur when they go for aligners, or the dental braces. So alternatively, there is an alternative method which was focused, which is nothing but the dental aligner. And the dental aligner was seen as a recent technology which came into existence to replace these traditional dental braces, because dental braces, once it is worn in, they need to stick to that for a continuous next 15 days, and then only they tend to fine tune it. But whereas, according to maxillofacial surgeons, if you are placing these aligners inside your mouth for once and continuously for 8 hours, that is more than enough to move or alter the mm, tooth inside. And wearing it for 8 hours, it is an easy job. Whereas for if we, every 8 hours we can't go to the dentist, so this becomes a tedious job. So that is why dental aligners were seen as a mechanism, as an alternate to the dental braces. So a person wearing this, they would wear it during night and they would go back to sleep. And once they are awake, they can remove it off and they can go ahead with their work. And again, for next rest of the time, they don't need to stick to the aligner. And after 16 hours, they can wear it for another 8 hours. So it keeps on changing. So that's how they tend to adopt these aligners. And the way how these aligners are made is, first, when they go to a dentist, a negative mold is taken. So you have a wax which is placed in a mold. The dentist would ask you to hold the wax in your hold this mold and bite it for a timeline of 20 minutes. The one very important thing over here is, when we bite it and hold it for continuous 20 minutes, our body is designed in such a way, our neural system will start moving once in every 30 seconds. Our body tends to move slowly. So that means that for every 30 seconds, whenever we move, it starts creating a clearance gap. And we know that this is going to be the mold which is going for real-time application. So as the gap tends to be widening, that means that we start losing our accuracy. So you can imagine that in a matter of 20 minutes, how many times we will be moving off. So the more we move, the more the clearance gap is going to be created. And based on this clearance gap only, the aligner is going to be manufactured. That is number one. Fine. Now, in spite of the gap that was created, or in spite of movements, they tend to take this mold, and after taking the mold, they tend to put plaster of Paris, and then they take the positive mold. And for this positive mold, by thermoforming method, an aligner is prepared. Like it goes with the vacuum thermoforming, and they get these dental sheets, bio-based dental sheets, which is 0.65 mm or 0.52 mm in thickness. They tend to get it from market, and they go for thermoforming. Once thermoforming is done, then they cut this with a sharp knife or a scissor, and that's how you are left with this dental aligner. And then they give this for to the patient. One very important thing is, when they start cutting it with a scissor or a knife, you would still have some sharp edges, and these sharp edges will start poking on the gums, and it will start creating more amount of bleeding. So as the bleeding starts, the patient need to come back the very next day. He need to get it fine tuned with the dentist, and then after a couple of days of iterations, then they tend to get fixed with this one of these dental aligners. So in order to fix one dental aligner, it tend to take at least 2 to 3 days for a patient. And like this, they have 15 sets of dental aligners for a generic tooth correction. So we realized that one thing is, it's a completely customized product. Variety is very high. Each one's tooth is aligned in a different way. And the lead time for this process is more than 48 hours. And more of a repetition, it tends to occur And still, no matter what, there is no accurate measurement that is undergone over here, or there is no accurate measurement that have happened here. It's all through an oral assumption or a visual assumption that dental tooth has been aligned. So then we came out with an option wherein using a dental scanner, or we have seen through the inputs for additive manufacturing, the entire scan is of the tooth is undergone. So the time that this patient goes to a doctor, an entire scan of his tooth is done. And when scanning is done along with the gums, the entire tooth is being scanned. So once it is scanned, we take this image to the geomagic tool, which we happen to come across in the inputs for additive manufacturing. So we move this entire file to geomagics, and in geomagics we tend to put this entire dental tooth over there. And now we got the profile of the gum, and based on the profile of the gum and based on the tooth, now we are in the moment we move to geomagics, it's again a CAD based software. Now I know that what is the angle that I need to rotate, what is the inclination that I need to alter. That is possible over here. Now we are speaking of exact accurate angles and exact accurate measurements that we can undergo. So based on that, the entire tooth profile is changed, and the gum profile is also very clear for us. So for this, I tend to just make a positive mold. All I do is I give a positive thickness to it, or again a positive thickness of 0.25 mm. So that means that according to the complete exact profile of the tooth and the gum, the part is made now. Once the part is made, Chalina is made, we go for a polyjet based printing. Um, and now this is the part which got printed with the support structure, and cleaning of the support structure, this is the final end part that is available. So this is for the first set. For the second set, I don't need the patient to be there. All I can do is I have the soft copy of the patient data, and I know that this tooth have been aligned. So once this tooth have been aligned, all I know that is these two tooths are going to be the reference for this third tooth. Now I would, based on this as a reference, I would realign this tooth according to the exact measurements, and again the process is repeated. So now we are speaking of a very high customization where the patient involvement with the doctor is only one time, and once in 15 days or 18 days he can come visit the doctor, he or she can get the data. So now if the scanning takes place in the evening, in a matter of 4 hours the part gets printed, and 100% accurate part is delivered to the customer, wherein it doesn't face any discomfort which they were facing at the earlier stage. And this gives a complete reduction in time of lead time, a complete reduction in terms of a hassle-free process. Um, so moving to the second case study, in this particular case study product, the lead time for the product arrival is about 18 to 20 days. This I'm speaking of is from the time they order the product to the time that they get the product. And the inventory of this product is held for a timeline of 2 to 4 months. And when this product fails, or when this entire product fails, this particular product will start creating a queue inside the system, and it causes a further delay. So this is a part wherein we worked on this part with one of the leading eye hospital in Coimbatore. So we all know that when we go for an eye inspection, first they ask us to check the pressure of the eye. So when they check the pressure of an eye, it is nothing but they have a plunger-like device. So you put your um, face, and they tend to bring a probe, and a certain amount of high pressurized air is injected on your eyeball, and from there they tend to measure the pressure of the eye. So for doing that, they have a plunger-like device, and this is the plunger-like housing wherein they press it maybe a couple of times in order to understand the reading of the eye pressure. So every day, at least some 200 patients have been tested on this. So that means that even if they press the plunger 5 times per patient, you are speaking of 1,000 plungers very easily. So once in 3 months, this entire device tend to get failed off. So here, in order to test it in this particular hospital, they tend to have some 15 to 20 devices. And even if one device fails, the queue starts building up as they go for other testing facility, because the queue starts building up. So then whenever there is an issue with this, they need to place the order to one of its supplier from German. And when the supplier tends to deliver the product to this particular eye hospital, they don't deliver the particular part which got broken. Usually the part that tend to get broken is this housing is the part which tends to get broken very frequently because of the continuous plunger movement. And when they deliver the part, they don't deliver this particular single part, they deliver this entire component together, which comes with the wall, which comes with an actuator motor. Everything comes in one single go. So this costs roughly about 15 to 18,000, and they need to wait for from the time they order to the time that they get this part. They need to wait for roughly about 15 to 18 days, and they get this entire part, and they need to spend quite a lot for getting this part every time. So there came a situation wherein they wanted to see whether it is possible to go for additive manufacturing application. So all we did is we took the data of this part, we measured it, and it has been completely 3D printed it, and the replacement was done straight away in a matter of 4 hours. Now we have the data of it. Whenever the part goes on, we tend to replace this part immediately within a matter of 2 hours. And earlier they were spending about 15 to 18,000 rupees on this. Now they end up spending roughly about 400 rupees on just this particular part, and their system is up and running. So here is one of the application wherein you don't need to hold the inventory on service-based products, and a digital inventory is perfectly fine in order to run the entire system, and your system doesn't stop at any point of time. You hold the digital data, you print it from there, you start using it directly, and it doesn't disturb the entire system. So if you look at it, ideally the entire market is moving towards reducing the lead time, reducing the inventory, and moving off more of a customer involved manufacturing. So speaking on these lines, we all know that yesterday Mercedes-Benz came out with the idea that at the moment already Lamborghini and Ferrari, they were using this model, and now that Mercedes-Benz have came out with this particular model in India, that you don't need to go to the seller or the retailer in order to buy their vehicles. All you need to do is you need to contact directly to the manufacturer. So contacting to the manufacturer, you can decide what you want to have in your dashboard. You are given an option to customize your dashboard, where you want your music system knobs to be, where you want your cup holder to be, where you want what sort of thing that you are looking at. You can decide, or you can completely customize your dashboard of your vehicle. And once you have decided it, it goes by virtual simulation. And once you're done with your virtual simulation, your product gets delivered, and you can pick your product. And as the manufacturer is directly in contact with the customer, now you are speaking of cutting off the dealer profits. So they're projecting that the cost of the vehicles are going to would possibly go by 20 to 25%, which is going to the dealers now. It would directly come back to the customer as a profit. So thereby they are trying to improve the sales of the part. The reason for the benefit for the manufacturer is now they are speaking of cutting off the inventory which is piled up across India. They have more number of retailers, and the inventory on those products are going to be cut off, and that is one positive way of looking at how they can change the entire spectrum of supply chain. And when they are going for this, now we are speaking of a completely custom built part or a completely custom built product at certain areas, and definitely a subtractive manufacturing system can't support this. So the only possibility or the easiest way to do it is through an additive manufacturing system. And already things, the automotive market have taken this segment and things are moving in that particular direction. So it is very clear that the shift in marketplace is taking place, and the with the internet, the entire spectrum have changed, and it is changing up at a very wide spectrum. Like now, most of the people would think like, fine, I could see it is possible, but where is that I can find the integration? And if you're thinking of where you can find the integration, the idea is one thing it is very clear is we know that there are n number of supply chains in the market space. The reason I call it as n number of supply chains is because there are n number of products. Because if you take just TV, a computer as a product, Dell has a different type of supply chain, Toshiba has a different type of supply chain, Asia has a different supply chain structure. So even one particular product type, a computer, it has n number of brands, and each brand has its own supply chain structure. Now, thinking of perishable products, it has its own different supply chain structure. Paper, a mature product, it has its own different supply chain structure. Like mass produced parts, it has a different supply chain structure. So, what is happening over here is if you try to mismatch your product and your supply chain will fail. So that is the reason why they grouped or they classified product into two types. One is the functional product and an innovative product. You need to understand the product that you're producing. Is it a functional or is it an innovative product? So if it is a functional product, then you need to think where you can bring your integration of additive manufacturing inside. If it is an innovative product, yes, you can straight away go for the integration. So this is rough classification which was done on the product type as either functional or innovative product based on the demand, based on the product life cycle, based on the product variety, and based on the average stock out, and based on the forecast error. Like having seen the product, and we know that supply chains are majorly it's of two types. One is the efficient supply chain, and the other one is a responsive supply chain. And we know that the product types are of majorly it's of two types. One is the functional or innovative. No matter whichever the company or whichever the product that you are manufacturing, your product will definitely fall within these two categories. Is either your product would be a functional product or your product would be an innovative product. If you're successful, that means that your product and your supply chain got matched together. If you are not successful in your product line, that means that there is a mismatch. Once you are able to match it with either an efficient supply chain nor a responsive supply chain, that is the first step of integration. Like, say, for example, like an efficient supply chain is steel industry. Like, it's a functional product. Your demand is possibly clear, your forecast error is less, so you know what your product is. So the moment your functional product is aligned with an efficient supply chain, you're perfectly fine. On the other hand, when we call it as an innovative product, your innovative product should be under the responsive supply chain. You can't make the customer to wait for a longer time. You can't say that I don't have your product, I can't give you the quantity that you're looking at. You can't change the quantities. But whereas in your functional product, you can claim that you will only give this particular quantity. You know your demand rate. But whereas in an innovative product, you don't know the demand rate and you don't know what is going to be the fluctuation of your demand. But only thing that you know is you need to have a responsive supply chain. You need to give what the customer asks immediately. So first thing to take away is align your product with the supply chain. Once you have aligned your product with the supply chain based on whether it is functional or innovative, whether it is towards an efficient supply chain or responsive supply chain, now you can think of the additive manufacturing integration. And when it comes to additive manufacturing integration, now you decide what is the supply chain that you have merged up with. And after that, you decide if it is your responsive supply chain. If you are in this efficient supply chain bracket, as the market have changed, as we have seen through the earlier cases, it is no more a seller's market, it is a buyer's market. So that means that you are obviously forced to move from an efficient to a responsive supply chain. So once you have moved to a responsive supply chain, you see, if you're looking for an additive manufacturing integration, you need to decide if it is a low variety, high volume product, you can't bring in additive manufacturing, or bringing additive manufacturing will lead to a failure. You can only go for an option wherein if you're looking at a very high variety and low volume, that is the place you would find additive manufacturing integration a positivity. If not, additive manufacturing would definitely fail over here. And not only that, the other important parameter is, because the cycle is repeating back, or our manufacturing cycle is going back to square one, wherein people started moving more towards customization. They want their product to be specifically designed or manufactured for their needs. And it is suitable. Now, let us say that you know that your product variety is high, your volume is low, and then you can have an additive manufacturing integration with the situation that your supply chain is going to be responsive. The final important parameter is what is the level of customization that you're going to go in. You need to look in what is the level of customization. Are you speaking of mass customization? And you can't stay with mass customization at this juncture. You need to go down in terms of level. From mass, you need to go to pure customization. From pure, you need to go down to core customization. From core, you need to move your scale to body fitted customization, or some cases you might go between core and body fitted customization. So those were the areas wherein your integration of possible integration of supply chain and additive manufacturing can take place. So the very primary thing is, or the key takeaway is, you need to decide what is the level of your product at the moment. If you can push the level of your product, no matter whatever the product that you're manufacturing, if you're able to push your product to this requirement or to this extent, then automatically it will find a fit in, or you can integrate with your supply chain. If not, you need to go back to your product, you need to push your product to this particular stage, and then only the possible integration can be made. So with that note, I'm pretty much fine with my presentation at the moment, and I'm pretty much open for questions. And I would like to thank the audience for their patient listening. And any questions, please? Any questions?
No, sir. Thank you. The presentation is very well clear. Thanks for that webinar, sir. Thank you.
Thank you, sir. Thank you.
Hello.
Hello.
Sir, I have a question, sir.
Yes, please.
Sir, what can I do for a startup entrepreneur? What kind of manufacturing business I can do, sir?
It is like ideally you need to decide on the product, wherein in terms of product you need to decide what sort of customization that you can do in terms of your product. And if you think that you can go as close as you can go in terms of customizing your product, like that is the space that you need to identify, and that would be because customization is becoming the future market. So if you are able to identify a product wherein you can get into customization and wherein you find the fit in of customization, that is the right place to start up with your product.
Okay, sir. Okay, sir. Thank you, sir. Thank you.
Um, like I saw a question by Prabhu Ramasamy, any source of rubber RPT? In terms of rubber-based RPT, you have a couple of sources in Chennai and in Bangalore. And earlier, any requirements, we do have at CAT, there is one rubber-based RPT machine as well. And if you need anything, you can, I'll share my contact details. You can send in your requirement. I can do that for you. It is possible for, in Coimbatore itself, it is available, and we have one of it. And Nirmal have asked a question, whether for casting 3D printing will be a suitability. Yes, like if you're thinking of making a core, or if you want to check the patterns, 3D printing can be used. And if you're looking for making tiny products or a product within the volume of less than 200 by 250 by 260 there are many sources that are available in and around Coimbatore wherein you can print your parts. Whereas if you're going to go for a higher dimension parts, then at the moment 3D printing would not be a suitability, because 3D printing at the moment, it has its own limitations and it can't produce parts to a bulkier size. Like anywhere, aluminum die casting 3D printing available. Like aluminum based 3D printings are available at the moment. In Trichy, in Bangalore, it is available.
Power off.
And it is there. But again, you need to decide if it is a minimum quantity that you're looking at, then aluminum, going for a 3D printing is a better option. But if you're looking for bulker volumes, I wouldn't recommend you to go for a 3D printing process. The traditional die casting would be a better process. But if you're thinking for, if you want to make an die which you're going to use for an aluminum die casting process, then in order to make the die, you can even go for a 3D printing process, because that would be a cheaper process as compared to you going to the die maker. Your 3D printing requirement would satisfy the work.
Sir, good evening. This is Puglendi here.
Yes, Mr. Puglendi, very good evening.
Sir, do you have any guideline to fix the volume? Like, because you are telling that the AM is suitable for low volume, right?
Yes.
So, do you have any guidelines to suggest for us?
No, sir. At the moment, like one easiest or one simple thing that we can speak is, let us say that if you're going to take a part, and even after making your die, you know that you would get your return on investment after printing some, let's say, for example, you'll get a return on investment after making 1,000 components. But if you think that 1,000 components is not possible, and you want to limit yourself within 500 or 200, and within that timeline, you want to make your part, during that situation, you going for a 3D printing process is optimal, provided if you know that you also know that you don't have an order above 1,000 quantity, then going for a 3D printing is a better option. But if you think that you would in this slot your requirement is 500, but in future you would get a definite order for another 500 or another 2,000 pieces, then you shouldn't go for a 3D printing as an option. So you fix yourself based on your return on investment. And within that limitation, if you're going for 3D printing, it is fine. But the moment you cross that, it is a very dangerous job to go for a 3D printing application. And always I would advise people not to invest straight away on a 3D printing machine, thinking that you can make more number of parts, because you having a metal 3D printer in your space is like having a white elephant. The reason is, whenever you go to a seller, they would give you an idea of mm, about only the mission. Let us say that they would say that this printer would cost you about 50 lakhs. But once you have got that printer, in India, the issue is even a slight variation in power factor will make your 3D printing to stop. Okay, let us say you wanted to print a part and you printed 98% of the part. Your printing is done, and a slight change in the power factor will stop the entire part, and now you need to restart the part from the beginning. So that means that the amount of time and money that you have spent is quite a lot. And when it comes to raw material, every time and then all these high-end manufacturers, you can't get the locally produced raw material. You need to stick to them for the raw material. And getting the raw material for 3D printing is quite a very expensive process. Like it is more or less like we maintaining our own color printer, because we know that once if you don't print a part for another 3 days in your color printer, the ink gets dried and your entire cartridge becomes as a waste. The same thing goes is applicable for 3D printing as well. The maintenance of it is quite a very expensive process, and that too for the metal printers, starting from the power unit to the post processing unit, to the clean room facility that you are going to maintain. It is like, let's say for example, if you're going to get a metal printer for 50 lakhs, you would end up investing a crore to your surroundings in order to maintain that 50 lakh printer. But if you are going to run as a service bureau, wherein you think that you are going to have continuous orders on certain products, then it is worth of investing that amount. But if you are going to be only one player in the market and you want to hold it of your own, then it wouldn't be an appropriate process. And on top of it, you need to have a well-trained professionals. That is where I was telling to the director of GKD ITR that he need to think, or he need to bring in a separate training process for people who can be used for 3D printing application, like as how you have the training for using the traditional subtractive machines. You need to have a separate type of training which you need to undergo for 3D printing machines as well. So I was mentioning about that to Dr. Balamurkan on that. I think very soon they are also planning to start one. So the essential thing is, number one is think before getting a 3D printer, and even then, you need to decide, even if you're using this service from outside space, you need to have some trained professionals inside your R&D who can say that I know that I can go for when I can go for a 3D printing process, and which machine would be suitable for my requirement. So you need to have a specialized, well-trained people to do that job. So without the knowledge of background knowledge of this 3D printing, I wouldn't recommend to go for a 3D printing process as such.
Thank you, sir.
Thank you, sir. In terms of aluminum, I know a couple of machines that are available for a volume of 400 by 200 by 180, 150 or 180, I think. Not more than that at the moment. Any other questions, sir?
Sir, this is Ram Kumar.
Actually,
I just want to know your views on 3D sand printers,
right,
which is used for course.
yes, that's right. Already one machine is there in SIMA, which is for 3D code printing. And like it depends, like if you're going for the continuous production process, then you can go for it. It is one of the very good options that you can go for 3D core printing, sand printing. At the moment, across globe, there are hardly about 100 or 110 machines which have been dispersed. For some reason, number one is because of the binder that they use, it tends to go off at a very faster rate, or the shelf life of binder is very less. So for that reason, not many people who have purchased, they went more on that. So, and secondly, the very important thing is it has its volume limitation. If you are, even at the moment, if you're thinking of core sizes less than 500 then you have printers that are available. Anything more than that, there are quite drastic limitations in terms of that. Yes, there are machines that are available, but one thing is the maintenance of those machines are very expensive. The reason is because of the binder that they were using to bind between one sand particle to the other sand particle, but the shelf life of those binders ranges from 3 months to 6 months. Anything, if you hold that binder for more than 6 months, it completely becomes as a waste. And those canisters are quite very expensive. That is why those people purchased it, they didn't go for that application after that. And secondly, you need to use only certain type of sand. You have a limitations because you can get the machine at a cheaper rate, but the raw materials are quite very expensive. And that is where they felt the limitations. You can have a view of those machines. It is available in SIMA, near to the GKD school. There is one machine over there. You can have a look at it, and then you can take it up from there.
Thank you, sir.
Thank you. Any other questions, sir? Okay. Like if you have any further questions, feel free to contact me either over the phone, or you can email me as well, or you can even contact GKD ITR for any further requirements on this particular process.
Yes, sir. Thank you very much for the wonderful session. Thanks for the entire information. The information was very useful. Thank you, sir. Mr. Rajesh.
Thank you. Thank you, sir.
For the tree of wisdom and knowledge covered us with during your amazing lecture. You are too excellent. We would like to thank our managing trustee, Madam Dr. Lailida Devi Sanjay Vijayavardhanavelu, and our director, Dr. Balamurugan Jam, for organizing this webinar break. Thank you. Thank you, everyone. We appreciate you being here. A recorded version of this webinar will be available in YouTube. We have loved to hear from you. Thank you once again. We will meet you next time. Thank you.
Thank you, sir. Thank you.
Thank you.